For 50 years, it has been a quiet, desolate neighbor, a place we visited, left footprints on, and then abandoned to the silence of the cosmos. But that silence is about to be shattered. We are no longer just visiting, we are moving in, and to survive there, we are bringing the most powerful force we have ever mastered. But here is the terrifying reality. The most dangerous thing about the moon isn't the vacuum of space or the radiation or the isolation. It is the darkness itself. And the United States has just confirmed a plan to conquer that darkness with nuclear fire. Recent announcements have confirmed what was once science fiction. By the year 2030, the United States aims to install a fully operational nuclear power plant on the lunar surface. This isn't just a concept art drawing anymore. It is a signed directive. In December 2025, President Donald Trump signed a decree mandating not only the start of construction for a permanent lunar base by 2030, but demanding that a nuclear reactor be ready for launch by that exact same date. Following this, in January 2026, NASA and the U.S. Department of Energy officially signed the Memorandum of Understanding to make it happen. With the first manned flight in half a century scheduled for early 2026, the clock is already ticking. But this begs the massive question, why? Why do we need nuclear power on a rock that is constantly bathed in sunlight? Why are we hauling a fission reactor 238,000 miles into the void? To understand why the United States is betting the house on lunar nuclear energy, we have to talk about the single biggest enemy of space exploration. It is a problem that has plagued engineers since the Apollo era. It's not the cold, it's the rotation. Here on Earth, a night lasts 8 to 12 hours. We have batteries that can easily bridge that gap. But the moon is different. A single day on the moon lasts 28 Earth days. That means for 14 straight days, the sun beats down relentlessly, and then, for the next 14 days, you are plunged into absolute freezing darkness. Imagine being trapped in a freezer for 336 hours straight, with no sun to charge your batteries, and the temperature outside dropping to minus 200 degrees Celsius. One mistake, one power failure, and the colony freezes. This is the tyranny of the lunar night. If you rely solely on solar panels, your lunar base is effectively dead for 2 weeks every month. You would need massive battery banks so heavy they would be impossible to launch on even our biggest rockets, just to keep the life support systems running until the sun rises again. And it gets more complicated. The Artemis program and the future US lunar bases are targeting the lunar South Pole. Why? Because that's where the water ice is. But the South Pole is a landscape of deep, jagged craters. Some of these craters have been in shadow for billions of years. If we want to mine that ice to create rocket fuel and drinking water, we have to operate in places where the sun quite literally never shines. Solar power is fantastic for the International Space Station, which sees the sun every 90 minutes. But for a permanent surface base, it is a logistical nightmare. The US isn't installing a reactor just to show off. They are doing it because without it, a permanent human presence is physically impossible. So, what is the plan? This isn't about building a massive cooling tower like you see in movies. The project, often referred to as fission surface power, involves a compact, ultra-resilient reactor. Think of it as a nuclear battery, but on steroids. NASA Administrator Jared Isaacman has stated that this technology is the key condition for long-term US space plans. And he's right. These reactors are designed to be relatively small enough to fit inside a lander, but powerful enough to generate 40 kilowatts or more of continuous electricity. Unlike the radioisotope thermoelectric generators, or RTGs, that power rovers like Curiosity, which run on the passive heat of decaying plutonium, this new project is a true fission reactor. It actively splits uranium atoms to generate intense heat, which is then converted into electricity. The beauty of this system is its indifference. It doesn't care if it's currently the 2-week lunar night. It doesn't care about dust storms blocking the sun. It doesn't care about the brutal deep freeze, it just runs. The mandate signed by the President and the Department of Energy requires these units to operate continuously for at least a decade without refueling. This creates a set-it-and-forget-it energy grid. Imagine the change in strategy here. We aren't just camping anymore. When you bring a nuclear reactor, you are building a city. You are enabling high-power experiments, industrial mining machinery, and comfortable habitats that require constant climate control. But make no mistake, this isn't just about science or survival. This reactor changes everything. It turns the moon from a graveyard of Apollo relics into a forward operating base for the ultimate goal: the invasion of Mars. Administrator Isaacman was very specific in his statement. He didn't just say moon, he said to Mars and beyond. There is a massive strategic layer to this announcement. We have to look at the language being used by the administration. Isaacman said, under the president's national space policy, America is committed to returning to the moon, building the infrastructure for a long-term stay, and making the investments needed to take the next giant leap forward. He called it the ushering in of a golden age of space exploration. This is language we haven't heard since the 1960s. But the context is different now. In the 1960s, the goal was a flag and footprints. The goal for 2030 is infrastructure. By signing the memorandum in early 2026, the Department of Energy has effectively been drafted into the space race. They are bringing decades of nuclear expertise to NASA's design table. This collaboration is designed to cut through the red tape. The timeline is aggressive. 2030 is just around the corner in aerospace terms. To have a reactor built, tested, certified for launch, and landed on the moon in 4 years requires a pace of innovation we haven't seen in decades. But the pressure is necessary. We know that other nations are eyeing the same strategic lunar real estate. The ability to generate megawatt-class power on the surface is the ultimate advantage. Whoever can keep the lights on during the long lunar night controls the territory. Mars is the ultimate horizon, but Mars is hard. It's far away, and the dust storms there can last for months, blotting out the sun across the entire planet. If we send humans to Mars, we cannot risk their lives on solar panels that might get covered in dust for weeks on end. The moon is the test bed. We need to prove that we can land a nuclear reactor, turn it on remotely, and have it run safely for years in a hostile environment. If we can do it on the moon by 2030, we can pack one up for the red planet in the late 2030s. Nuclear propulsion and nuclear surface power are the two technologies that actually unlock the solar system. Chemical rockets and solar panels can only take us so far. If we want to go deep, to the outer planets, to the dark caves of Mars, to the oceans of Europa, we need the dense, raw power of the atom. There are, of course, immense challenges. Launching nuclear material into space comes with rigorous safety protocols. The reactor will likely launch cold, meaning the uranium is inert and not radioactive until it lands on the moon and is switched on. This ensures that even in the worst-case scenario of a launch failure, there is no risk of nuclear contamination to Earth. This is the level of engineering NASA and the Department of Energy are tackling right now. We are standing on the precipice of a new era. The return of manned flights is the opening ceremony. But the reactor project, the installation of a power grid on another world, is the main event. It signifies that humanity is done with visits. We are ready to stay. The United States has drawn a line in the lunar dust. By 2030, a new light will turn on in the darkness of the lunar South Pole. A light powered not by the sun, but by American engineering and nuclear physics. It's risky. It's expensive. And it's incredibly difficult. But as we look up at the moon tonight, we know that the silence is ending. The engines are warming up, and the golden age is just beginning. If you enjoyed this video, please hit that like button and subscribe. It really helps the channel out more than you know.